All right, good morning, chemists. We'll get started and continue our conversation of electrochemistry, but a couple announcements. So tomorrow, Friday, is recitation 9, which is a graded attendance activity. So show up, get your points, do some practice problems, reviewing electrochemistry with your TA. But then the following recitation is midterm 4. And as always, I'll hold a review session on Tuesday in the evening. I haven't posted anything because I haven't made the packet yet, but just understand that the review session will happen at the normal time. I'll post the links and all of that when I create them. What was the other thing I was going to say? Oh yeah, the lecture video from Tuesday. I lost power while it was uploading, and so it paused. It interrupted the uploading process, but now it is finished. I had to resume it, so that lecture video from Tuesday is now posted. All right, so let's review a little bit of electrochemistry before we kind of dive into the more details of electrochemistry. So just kind of review those core concepts that we talked about earlier this week and last week. So I have a redox reaction here. It's quite simple with just generic things. So let's inspect it and try to look at the details of what happens in a redox reaction. So we see that A plus, a cation, come on, pen, are you dead? A plus cation is being converted to a solid, and B solid is being converted into its cation. So A is being what? No, it's not being oxidized, it is being reduced. Because if we look at these oxidation numbers, we can see it's very closely related to charge. So +1, 0, 0, +1. So we see that A, its oxidation number is going down, so it's being reduced, while B, its oxidation number is going up, so it is being oxidized. All right? A plus is gaining electrons, while B is losing electrons, giving its electrons to A plus. So that makes A plus what kind of agent if it is being reduced? It is the oxidizing agent, while B solid, therefore, is the reducing agent because it is giving up its electrons to give to A plus to do the reducing, all right? Okay. So that's just kind of inspecting oxidation numbers and categorizing your reactants as either being oxidized or reduced, and oxidizing agent, reducing agent. So that's a skill there where the ideas of reduction and oxidation and agents are very closely tied to one another. All right, so now let me give you numbers. So the same reaction. Here, I give you reduction potential. So if you go to the book and you look up potential, whatever, if you go to the textbook and look up values for these chemical half reactions, you'll always find reduction potentials. You're not going to find oxidation potentials. But the problem is both of these reactions, these half reactions, they're both in the reduction form. But we just noted that A plus is being reduced, all right? So the A plus half reaction will work here, but B solid is being oxidized, but I give you a reduction half reaction. So this is the idea that, you know, in a redox reaction, reduction and oxidation occur, but we give you values of just the reduction values. So when we calculate the overall cell potential of the chemical cell at standard conditions, we say that E cell equals the reduction potential at your cathode minus the reduction potential at your anode. That minus sign does the flipping for you as long as you identify what your anode and cathode are. So we already identified what's being oxidized, what's reduced, and so I had you memorize that red cat. So A plus is at the cathode, while B is the anode. So that is the half reaction happening at the anode. So when we calculate the overall cell potential of this chemical cell as written, we see that A plus is being oxidized, A plus is being reduced, so it is the cathode. So E cell is equal to 1.0, that's my cathode, minus the reaction the reduction half reaction that's happening at the anode. So we're going to subtract 0.4, all right? So the overall cell potential, if we were to set this up at standard conditions, so 1 molarity of everything, we would read something like 0.6 volts for this chemical cell, all right? So kind of extending the idea of identify what's being oxidized and reduced, and there you have it. You have your anode and your cathode to do that math once you have those reduction potentials. All right, so let's move on a little bit. So let's see if we can't interpret these reduction potentials. So tell me, let's compare the reduction potentials of the A and B compounds. So based upon these numbers, all right, we want positive voltages. Positive voltages mean spontaneous, and we'll learn about why that is in a moment. So based upon these reduction potential values that I have given here, A plus, come on, highlight. A plus is what, how is its reduction compared to B plus? Is it more or less easily reduced based upon these numbers? What do we think? It is more, yes, it is more likely to be reduced because its reduction potential is higher for A, all right? A's reduction potential is higher. It's more spontaneous, all right? So it's more easily reduced because I'm giving you reduction values. So that makes A plus a better or worse oxidizing agent. So remember, reduction also means oxidizing agent, so this would mean A plus is a better oxidizing agent. Remember, reduction and oxidizing agents, those things go together. So if a question on an exam says, you know, what's more easily reduced or what is the better oxidizing agent, those two questions are the exact same question. That's what I want you to get at. It's assessing the exact same concept. Oxidizing agents are very easily reduced, so you're trying to find very positive reduction potentials, right? Okay, so let's keep going, but let's talk about oxidation and reducing agents because it's kind of the opposite, all right? Okay, so here are the same two reactions. There's A plus, B plus, the reduction potentials, but they're in the reduction form. So let's think about it. What if A and B were oxidized instead? So instead of gaining electrons, let's say they lose electrons. So basically, we're doing the reverse reaction here. So you can think a reduction half reaction is the opposite. You flip a reduction half reaction to make an oxidation half reaction. So you see I've rewritten these reactions now in the oxidation form, but they're simply the reduction reactions flipped, where now the solid is losing an electron. So what do you think the potentials are for these oxidation half reactions? So technically what we're calculating here is the oxidation half reaction. Technically, you'll never find this in a textbook, but you have to infer what these values are. If we flip a reaction, we're also just going to flip the sign of that value. So the new value for oxidation here for A is not 1 volt, it is actually negative 1 volt. And then the oxidation half reaction for B, its oxidation potential is negative 0.4. So are these very spontaneous reactions? They're not. All right, in the oxidation form, these reactions are not as spontaneous because they're negative values, right? Okay, but let's see if we can't interpret these half reactions now. So notice how now I'm comparing A solid and B solid because in an oxidation reaction, those are what the reactants are now. In a reduction reaction, the cations were the reactants. So I'm comparing like A plus and B plus, but in an oxidation reaction, those solids, the products from the previous equations are now the products, are now the reactants. So here I'm comparing A solid and B solid. So what can we say about the oxidation of A versus B? A is what, is it easily or less easily oxidized than B based upon these numbers? It is less easily oxidized than B because the oxidation value for A is more negative. It is more negative, all right? So that means A solid is a worse reducing agent than B. So B solid would be the better reducing agent here because it has a more positive oxidation potential. All right, okay. So kind of like if I go back to these reduction half reactions, remember when we talked about like acids and bases, if you have a weak acid and it's a strong weak acid, its conjugate base is a weak base. Kind of the same thing here. For a reaction that is highly easily reduced, so for like A plus is very easily reduced. So that means A solid is not very easily oxidized. But here B is less easily reduced, so therefore B is more easily oxidized. So kind of that backwards thinking again shows up here as well. Okay, is that good review? Okay, so let's put it all together. And let me ask you this question. All right, so same thing, okay? Here's a different reaction between X and Y, all right? So these are both reduction values, those are the numbers. So which substance is the most easily reduced? X plus, Y plus, X solid, or Y solid? What do we think? So what are we looking for if we want to find the thing that is most easily reduced? We want the reduction potential that is the most positive, yes. So that would be the first, no, that would be the second reaction, right, is the only positive one. But you gotta be careful, which substance do I wanna point at? Is it Y2 plus or the Y solid is the thing that's being reduced in that reaction? It's the cation. So in this case, it is Y2 plus is the most easily reduced. Okay, so you're looking for the reactant that's in the most positive reduction reaction. All right, so then therefore, and then the follow-up here, all right? So I asked what is most easily reduced, or I could reword that question to say what is the most easily oxidized, and it's literally the same answer. All right, so both of these questions have the exact same answer, because our approach is the exact same. So if I was asked on the exam what is the best oxidizing agent, I would reword that in my brain and think, okay, which one is the most easily reduced? And so therefore, I'm looking for the most positive reduction potential substance. All right, so both of those questions are the exact same. So just like in the next one, which is the most easily oxidized or what is the best reducing agent, that's the same question. But we're looking for something else, right? What we're looking for is the most, I guess, positive oxidation reaction, but those values aren't given. We are given reduction values, so you have to flip them, all right? So based upon this, Y plus was the most easily reduced, so it's going to be an X substance that is the most easily oxidized. But which substance is being oxidized? X solid or X plus? The solid, yes. Yes, it is the solid. So you're looking for the most positive oxidation value or the most negative reduction value, but again, you want to point to the product because you have to flip the reaction for an oxidation reaction. All right, so I hope that clarifies things as you do homework for this next section. Those are kind of some conceptual things that you can work through. That really don't require any math, but really require a deep understanding of reduction and oxidation. All right, and so hopefully going over this will help if you review these slides where we looked at these half reactions and compared what was most easily oxidized. Okay, so we will continue on with the remainder of chapter 20, where we'll cover the last two sections on midterm 4. All right, so just as a reminder, parts 1 through 6 are on midterm 4, and then these last 3 sections are on the final. We'll probably finish up the rest of this chapter next week, but just like last time, we'll kind of move through the remaining chapters slowly because I'll incorporate a lot of review next week. Okay, so let's talk about free energy. Okay, so Kay is back. All right, Kay is back. I'm sorry. She went away for a little bit, but now she's back. So we've been talking about spontaneous reactions, spontaneous redox reactions. We know a redox reaction is spontaneous when E cell is what sign? Positive. We were always looking for positive signs of E cell. So we're talking about spontaneity. So if this reaction is spontaneous, just predict what should the sign of delta G be? Negative, yes. And so there's a relationship we'll talk about in the next slide. Or you can think, what is delta S of the universe change for a process that is spontaneous? If this redox reaction is spontaneous, delta S of the universe should also be a positive sign. All of these things relate to one another, and it'll come all together in the next slides. Okay, so I should mention what is exactly voltage. So voltage is basically the energy difference of your products and your reactants. You can kind of think about energy. So if you look at some type of electrical device, you'll oftentimes find a voltage, but you'll also find a current. Both of those values and measurements are completely different from one another. Voltage, and the analogy is like a waterfall. All right, voltage is how high your waterfall is, how, you know, the height that the water makes, all right? Like if it's a really, really big waterfall, that's a really big voltage drop difference. That's what voltage is. It's like an energy, I like to think of it as like an energy difference. Current is something else, but it's also a component in electrical devices. Current is how fast your electrons are moving through, how fast and how many electrons are moving through like your wire or whatever. So current, if we go back to our waterfall analogy, is like, I guess, how wide your waterfall is. So if it's just like a very, very small stream, if you count the number of water droplets, pretend like a water droplet is like an electron. If you have a very, very small stream of water, that would be a very low current, versus if you have a really wide waterfall, that's a really high, large current, because you're moving a lot of electrons or a lot of water with time. So that's kind of the analogy here. In terms of like danger when it comes from electricity, it's not the voltage that kills you, it's the current that kills you. It's how much electrons are moving through your body at once. It's not necessarily the voltage drop. That's there. And so we'll talk about current at the end of the chapter, but just to introduce it, current has to do with how many electrons are moving through your circuit at any one time. And so we can quantify this using Faraday's constant. All right, Faraday's constant is the unit, it's right here. Here's the unit of Faraday's constant. All right, where 1 mole of electrons is equal to 96,485 coulombs. All right, we can't count electrons, we can't see electrons, but we can measure coulombs, we can measure charge. So if we know how much charge is moving through our circuit with time, we can convert it using coulombs, use Faraday's constant to convert to, okay, how many electrons do I have present right here? So we can measure coulombs, and then we can relate that to how many electrons are involved in this process. All right, so we'll be using this Faraday's constant a little bit in the next slides, but understand this is a constant. We give it to you on the exams, but this is the significance. We can't measure electrons directly, but we can measure coulombs. All right, and current is, the unit here is amperes. We'll talk about this at the end of the chapter. That's not super important right now. What is Faraday's constant that we'll be using here in a little bit. Okay, so just like what we did Gibbs free energy calculations, when we used table values, we assumed we were at standard conditions, meaning 1 molarity, 1 ATM, 298 Kelvin for everything. So we can set up electrochemical cells at standard conditions as well. 1 molarity of everything, 1 ATM of everything, 298. But do we have to set up our cells? Do we have to set up our batteries using 1 molarity of things? No, we can use whatever concentrations we want. But then the calculation is a little bit different. When we're in non-standard conditions, we actually have to use what we call the Nernst equation that takes into account those concentration differences that deviate from standard conditions. All right, so let's answer the question, why are positive cell potentials spontaneous? we saw that, oh, when the cell, overall cell potential is positive, it's a spontaneous redox reaction, so therefore delta G of that reaction has to be negative. And here's the reason. Here is the relationship. Delta G for a reaction, if you have the cell potential for it, or the voltage, is delta G is equal to negative N. So N is the number of electrons in the process, right? F, so Faraday's constant, this allows us to convert it into an energy term, voltage into an energy term, and then times the cell voltage for that process here. So this, you can see delta G and E are related by a negative sign. So anything with a positive E is going to have a negative delta G. And so that's why we were always looking for positive E values to mean spontaneous in the forward direction. So you were kind of doing that subconsciously all this time, but the reason is because of this equation right here. Positive E's give very negative delta G's, and to us, back with chapter 19, means spontaneous. All right, so everything is interconnected via delta G. All right, so in last chapter, we talked about this equation. Delta G, Gibbs free energy of a reaction, is related to its equilibrium constant. We did delta G equals negative RT ln K. The new idea for this chapter is that E is related to delta G in terms of to predict spontaneity. So we have three different kind of variables here, or three different properties. E, our voltage, delta G, Gibbs free energy, and K. So if E is related to delta G and delta G is related to K, that means E is also related to K as well. And it's related by the Nernst equation. So we can actually combine these two reactions and rearrange things and get a relationship between the cell potential of your electrochemical cell and the K, the equilibrium constant for that reaction as well. It's related by a factor of RT, just like delta G, but because it's an energy or a voltage term, we also have to include NF. Again, N means number of electrons involved in the process, and F is Faraday's constant. So the idea here is that these three terms, they are all related to one another, all right? That delta G and K, we already know they're related to one another. The magnitude of your equilibrium constant, whether you have a lot or a little bit of products, is related to the sign of delta G. E is related to spontaneity, and so our electrochemical cells, K, equilibrium constant, they're all related. Okay, so here are all the equations at standard conditions that we've collected so far, right? E cell is cathode minus anode. That's when we use table values. But remember, if we use table values, that's at standard conditions, meaning we have 1 molarity, 1 ATM of everything. So if you do cathode minus anode, you are calculating the cell potential when you have 1 molarity of everything. But we don't have to have 1 molarity of everything. We have this new equation, relates delta G and E, and then we can relate E to K as well. So just like in chapter 19, we could calculate delta G at standard conditions, right? This was delta G naught, that was at standard conditions. That's when you use the textbook table values and just did products minus reactants. We could also calculate Gibbs free energy at a certain condition, not at standard conditions, using Q, where Q represents the concentrations you actually have. And then you got a new delta G, and you were able to predict, does the reaction move forward or in reverse? So just like we did for delta G, calculating delta G at non-standard conditions, notice that there's no naught here. We can do the same thing with our cell potential. Cell potential without the naught. See how this E has no naught? It means we're not at standard conditions, meaning our concentrations are not necessarily 1 molarity and 1 molarity. So we can use this equation. This is the Nernst, oh, I wrote it right there, is the Nernst equation, where we calculate the cell, cell potential of our electrochemical cell is equal to what the cell usually is using book values. So here, this is our normal cell potential. So here you just do, cathode minus anode. But then you need to take into account what are the actual concentrations present. So you subtract this voltage divided by N log of Q. So this value right here, 0.0592 volts, is basically RT when T is equal to 298. So we just did the math for you. It's RT over F, sorry. RTF at 298. That's just a constant as long as RT over F at 298. So this whole term is a constant as long as your temperature is not changing. R is a constant, F is a constant, T, if it's at 298, it just stays constant. So we just did the math for you, and we can simplify the Nernst equation to say that 0.0592 over N is related to the log of the concentrations actually present in your electrochemical cell. So I want you to draw parallels between cell potentials at non-standard conditions and delta G at non-standard conditions. They're related to one another. It's actually the same equation. All right. Okay, so let's think about the relevance of this and how batteries operate. How batteries operate and how electrochemical cells operate. So here I have a redox reaction between zinc and copper again. Right, so this balanced redox reaction, zinc is being oxidized, so it's the reducing agent. Copper 2+ is being reduced, so it's the zinc is being oxidized, so it's the reducing agent. Copper 2+ is being reduced, so it's the oxidizing agent. Great. So when this cell is made up at standard conditions, it has 1 molarity of everything. We got that the cell potential was positive. So let's just check again. Here's copper. My copper is being what in the reaction? Copper is being reduced, so it's the cathode, and then zinc is our anode, and so yep, we see a positive cell potential, and then let's just let this spin for 80 minutes. All right. We're harnessing that positive cell potential and the electrons that are moving from products to reactants as well to run our little thing. All right. That our voltage drop here is 1.1 volts because we're at standard conditions. So if we're at standard conditions, all of the concentrations are 1, and what we'll actually get is that Q is equal 1 at standard conditions. So that's why if I measure with the voltmeter the cell potential, if I put those alligator clips on the cathode and anode, I should read a voltage of 1.1 because we're at standard conditions. But let's think about what happens as the reaction moves forward. So right now, when we start the reaction, at standard conditions, Q is 1. Because if you calculate Q is no different than the Q we talked about in chemical equilibrium. It's products over reactants, so the only things that are in our Q expression are zinc 2+ and copper 2+, products over reactants. But what we see here at standard conditions, this value is 1 molarity, this value is 1 molarity, so Q is 1. But let's think about how these numbers change with time, because right now, yes, electricity is running through this, but where's that electricity coming from? It's coming from a chemical reaction that's happening right now. So as this reaction proceeds, how does the concentration of the zinc cation change? Look at the reaction. Zinc 2+ is a what? It's a product. So zinc 2+ concentration is going to go up. Yes, it's going to go up, increase. So that means copper 2+ concentration is going to do what? Decrease, because it is a reactant. So is the value of Q going to change as this reaction goes forward, or is it going to stay 1? It's not going to stay 1. It's going to go up. So we see that Q actually increases as this cell runs. Okay? If you let the cell run long enough, and if Q changes, if you look at the Nernst equation here, okay, so here's our Nernst equation. If Q becomes a bigger number, we're going to subtract a bigger number from E cell at standard conditions. So we're going to see that E cell, what we actually measure, is going to decrease over time, right? All batteries die eventually, right? And this is why, because you're using up your reactants, making more products, you're changing Q. So your cell potential, your measured cell potential starts to decrease and decrease and decrease until it becomes 0, right? And so the reason that when we're at standard conditions, so let me just show you here with this equation and just use math. So at standard conditions, Q is equal to 1. What is the log of 1? 0, yeah. So if Q is 1, this whole term is 0. So the cell potential that you measure is equal to the standard, the E naught. So E naught comes from the textbook, cathode minus anode. And so that's why when you're already at standard conditions, you have 1 molarity of everything. What you measure is the textbook value. And that's because Q is 1 at standard conditions. All right. So all right, so let's do some calculations using the Nernst equation. So this is, again, not at standard conditions, typically meaning that we have concentrations that are not necessarily 1, and we have to use Q instead to calculate what the overall cell potential is. So there's a process here. Just like when we did delta G, typically what we have to do is calculate delta G naught first, so delta G using the table values, and then we have to incorporate Q into that. So it's the same thing here. I give you a chemical reaction. First, we need to calculate E naught, so the cell potential at standard conditions. Then we need to incorporate Q. So here, I have a pretty complex chemical reaction, but I've done the balancing for you, and I've given you the 2 half reactions that are involved, and I've given you the reduction potentials. So first, let's calculate E cell at standard conditions for this reaction. So let's just use the table values. Cathode minus anode, but that means we need to determine what is our cathode and what is our anode. And then what I want us to do is let's calculate the cell potential at these conditions. So these are non-standard conditions because not all of the concentrations are 1, so we have to use the Nernst equation. So E cell naught, so this is table values. I give you the reduction reactions, but we need to figure out what's our cathode and what's our anode. So I'm just going to do the easy one here. I see I minus is going from a -1 oxidation number to a 0. So I minus is being what? Oxidized. So I minus is the anode. So that means this reaction, the second one, is our anode. So that means the chromium half reaction has to be our cathode. But we can check it too. So this one has to be our cathode, but we can check it. I'll do a different color here. Chromium in the product side is +3 because it's just chromium +3. But this chromium is a little bit more complex. There's 7 oxygens. So that's a -14. And all of this has to add up to -2. So that means these 2 chromiums have to be a total +12. So that means 1 chromium is what oxidation number? +6. So chromium is going from +6 to +3. So it is being reduced. It is the cathode. But we could have done process of elimination as well and gotten the same answer. So yes, chromium is the cathode. Iodide is the anode, so if we calculate the overall cell potential, it's going to be 1.33 minus 0.54, and that is, what is that, 0.79. All right, so if we had 1 molarity of everything, and we hooked this cell up and measured it, we would measure 0.79 volts. But the follow-up question is, well, we're not at those concentrations. We have different concentrations. So we have to use the Nernst equation at these non-standard conditions. But we still need to use this E cell naught value in the Nernst equation. So we can't skip the cathode minus anode step. Because here I give you a bunch of concentrations. So it's in our best interest to calculate what is Q at these given conditions. So what we need to calculate Q is the full chemical reaction, and we need to do products over reactants, just like before. All right, so I have that balanced chemical reaction here for you. So Q is equal to the chromium concentration, but it's squared. Anything else in the numerator? Nope. No liquids, no solids in Q's. Remember, Q is the same as K. Over my products, so my products are chromium, that chromium oxide compound. So one of those, I have 14 H pluses. So this is the H plus concentration to the 14th power. Yes, 14th power. Yeah, dang. And then I minus to the 6th power. All right. But no problem. We know all these values. You were given all these values. No, we know that, we know that, we know that, and we know that. So just plug them all in and calculate what's Q at these conditions. Because at standard conditions, Q is just 1, and we can go ahead and just do cathode minus anode, but here Q is something else. So let's plug in those numbers. We get that Q is equal to 1 times 10 to the negative 5 squared over chromium concentration. So 2 times H plus concentration. So 1 molarity to the 14th power. Thank goodness, that's just 1. 1 to the 14 is just 1. And then I minus concentration is also 1. So 1 to the 6th power. All right, so that's not too bad. So we see that Q is equal to 5 times 10 to the negative 11. All right, and so we're going to use that Q value and the Nernst equation and just plug and chug here. Because we know, here's our Nernst equation. So the E cell that you actually measure is equal to E cell at standard conditions, which we know, we did that in the first step, minus that voltage over N log of Q. We know what Q is, we just calculated it. Now we need to figure out what N is. All right, so we need to figure out how many electrons are being transferred during this process. There's a couple ways you can do it. If you look at the 2 half reactions, notice that the first half reaction utilizes 6 electrons. And then the second reaction utilizes two electrons. So if you wanted to, flip things and balance it, we would take that first reaction as is. The second reaction we would flip, but we would also have to multiply by 3 to make those electrons match. And the number of electrons that match is 6. So in this case, N is equal to 6 in this reaction. Do you see how I got that? So I really didn't have to fully balance the reaction. I just kind of look at the half reactions and I say, oh, okay, 6 is the lowest common multiple of those. Or another way you can figure out how many electrons are being transferred. Look at one of the half reactions. So there's like I minus in the balanced reaction. You're starting with 6 I minuses, so that's a total negative 6 charge, and you're making 3 I2 solids, which are charge neutral. So I see, oh, I minus is losing a total of 6 electrons. So N is equal to 6. So it works that way as well. Okay, so N is 6. So now we have everything. We just plug and chug. So E cell at these non-standard conditions is equal to 0.79 minus 0.0592. Volts over N, we just got a 6 log of 5 times 10 to the negative 11. All right, and then you get that the cell voltage is, ooh, look, a little bit higher. We were able to get a little boost in voltage just by adjusting those concentrations. All right. Okay, so that's the strategy here. Start with the book value E cell not, doing cathode minus anode, get Q values, figure out what N is, and plug into the Nernst equation, just like we did delta G at non-standard conditions. Okay, so let's do another one, where instead of calculating E cell, I'm gonna ask you, okay, here is the E cell. You set up this reaction, there's the E cell, here are some concentrations, tell me, what is the pH of this solution if this is the cell potential that we measure? So we're still using the Nernst equation, we're just solving for something else. Because in this example, this time I give you what the measured cell potential is. We still know what the cell potential is at standard conditions. We already know what N is, we already got that, N is 6. It's the same reaction. This time we're solving for Q. And if we remember what Q is, look, Q has H plus concentration in it already. And if you look at the last bits of information that's given, yes, I in fact give you the chromium 3 plus concentration, it's right there. I give you the I minus concentration, and I give you the chromium oxide compound as well, right? So in this question, we are solving for Q given the variables, the measurements that I give you in this question. All right, so same exact process. I give you the cell potential already at standard conditions. All right, so what we're going to do is just rearrange things and isolate Q and figure out what does H plus have to be in order to achieve that Q value. So E cell equals E cell at standard conditions minus 0.0492 volts over N log Q. And so again, we know all of these values. I'm going to solve for Q in this case. So the measured E cell is 0.81 minus what the equals the E cell what it usually is at standard conditions, so 0.79 minus 0.0592 over 6 log Q. So when you solve for this, we get that, what is this? Where's my work? Positive 0.02 equals 0.0592 over 6, there's a negative there, log Q. And so I'm going to multiply by 6, divide by negative 0.592. So then I get rid of that coefficient there. And so on the left side, I get something like, what did I get? Oh, negative 2.2027 equals log Q. All right, how do I get rid of a log? 10 to the, yeah, so if you do 10 to the both sides, you get rid of that log. And so you get that Q is equal to 10 to the negative 2.2027, or Q is equal to 0.009396. All right, so that is the ratio of products over reactants in order to get this measured cell potential. That's a little bit deviated from the cell potential at standard conditions. That's not our answer. Now we need to plug in the actual known concentrations into that Q expression. So Q is equal to chromium concentration. I already tell you it's 10 to the negative 5 squared over the chromium oxide concentration, so 2 molarity, times H plus concentration, that is what we are solving for, times I minus concentration, so this is, I think it's just 1. Perfect, and is equal to 0.009396. So we are solving for H plus, which is in the denominator. I don't like that. So I think you move things around and you get H plus to the 14th power is 0.009396 times 2 over 1 times 10 to the negative 5 squared. And so that is equal to what? 5.3 times 10 to the negative 9. Okay, but this is H plus to the 14th power. How do I, should you spend time and look for the 14th root on your calculator? No, so how do we undo the 14th power? Take both sides to the 1/14th, 1 over 14th. So into the 1/14th exponent here, and that's how you undo that H plus. So if you do that, if you do 5.3 times 10 to the 9 to the exponent 1 over 14, you get that H plus concentration is 0.59 molarity. And then if you pH that, you get that the pH is less than 1, it's 0.59. So it's quite acidic, quite acidic. Right, so this question, really no different than the previous one. We're just utilizing the variables a little bit differently, where we're solving for a component, a concentration in the Q expression to give this measured cell potential. Versus in the previous question, I gave you all the concentrations at non-standard conditions and you just poop out a cell potential. So this one's really no different. A little bit more complex because we're solving for what's inside the logarithm. All right, so let's keep going. Let's do another one. So here is a reaction. It's at standard conditions initially. Here are your reduction potentials. Let's calculate delta G at standard conditions, and K at standard conditions. So the idea here, if you think about the equations that we're going to use, if I just give you this information, you can, yeah, go ahead and calculate E cell, right? E cell not, because we're at standard conditions, but E cell not tells us a lot of other things as well. E cell not is also related to the delta G of a reaction. Delta G of the reaction is also related to K. So if I give you a electrochemical reaction and ask you to calculate delta G or K, your first step is let's calculate cell potential first. So you have to do cathode minus anode. In this case, we're already at standard conditions, so the Nernst equation is not necessary at all. We just need to calculate E cell. So we need to determine what is the cathode and what is the anode. So if you get oxidation numbers, silver solid is 0, silver plus is +1. So the silver half reaction is what electrode? The anode, because it's being oxidized. So therefore, O2 has to be the cathode, right? So if you calculate that, the standard cell potential, if you do cathode minus anode, is 1.23 minus 0.8. So we get something like 0.43 volts. So at standard conditions, this reaction is spontaneous because it has a positive cell potential. And so let's calculate delta G and K using this value we just got. So the equation that we're going to use first to calculate delta G is delta G equals negative NF, the E that we just calculated, right? So we know E cell, we just got that. F is a constant, we just need to get N. So based upon these two half reactions, how many electrons have to be transferred? 4, yes, because the first reaction requires 4, the second reaction requires 1. So if we would have balanced these half reactions, I would have quadrupled the second one and flipped it in order to add them up. So N is equal to 4 in this case, right? So now it's just plug and chug. Delta G for this reaction is negative N, so negative 4 times Faraday's constant, so 96485 coulombs per mole, and then E cell, which we just calculated, is 0.43 volts. Okay, mole. All right. And I know that these units look all weird, but this is simply delta G. Delta G has what unit? Joules. It's just an energy unit. So the value that comes out of here is also a joule. So yeah, a coulomb times a volt is a joule that comes out if you look at the SCI units, the SI units. So if you just multiply these numbers together, you will get a joule value that comes out, and you get something like delta G equals negative 165.9 times 10 to the 3 joule per mole of the reaction, right? Or you can think negative 165.9 kilojoules per mole, whatever, right? And so if this was chapter 19, you would say, yes, this is a spontaneous reaction because delta G is negative. Perfect. But delta G can tell us other things as well. Delta G can also tell us information about K, the equilibrium constant. So now that we have delta G, we can use the equation delta G equals negative RT ln K to calculate what is the equilibrium constant for this reaction as well. So we already have delta G, R is a constant, T is what if we're at standard conditions? 298, yep, so we just have one variable solve for K. So simply negative 165.9 times 10 to the 3 joule per mole. So remember, R is in joules, so keep delta G in joules as well, equals negative R, so 8.314 times K, 298, ln K. Oops, ln K. So you solve for K and you get a really big number, 1.1 times 10 to the 29. So this reaction very much favors the product side. It wants to go to the product side, right? Because K is a really, really big number. So it makes sense that this reaction is spontaneous. If you mix these things together, K, that really big value of K and negative delta G is going to push the reaction in the forward direction to make more products in this case. Because what we see, if we're at standard conditions, all of these concentrations equal 1 molarity, Q is equal to 1. So at standard conditions, we start with equal concentrations, but the reaction really tends to go in the forward direction, which is why our cell potential is positive, and this reaction does proceed in the forward direction as predicted, because K is a big number, delta G is a very negative number, and E cell is positive. Because if we start at standard conditions, we don't have enough products, so the reaction moves forward to achieve that. All right, so again, relating E to delta G to K, all of it's related. All right, so let's just do a couple more here. Okay, so in the previous question, we did this reaction at standard conditions. So Q is equal to 1 at standard conditions. So now let's do this question at non-standard conditions. Let's say we're doing the same exact reaction, all right, so the oxygen and silver thing, and I already gave you E cell since we calculated it already. What if instead of setting it up to standard conditions, what if we set it up so Q, the concentrations of the cell is actually equal to K? What if we force Q to equal 1.13 times 10 to the 29 and calculate E cell and delta G? So here we're going to use the Nernst equation because we are no longer at standard conditions, we are at non-standard conditions. I give you Q, so you want to use the Nernst equation. So here is the Nernst equation. We're calculating the cell potential at these given conditions. We know E cell at standard conditions. We already know what N is, and you were given Q. So it's just plug and chug right now. So E cell, what we actually measure at these Q conditions is equal to E naught, so 0.43, we just got that, minus 0.0592 volts over N. It's the same N as before, so it's 4, I think. Yeah, it's 4. Log of Q. So I'm telling you that you set this cell up so Q is equal to 1.13 times 10 to the 29. So I didn't necessarily give you concentrations, but I gave you the ratio of the concentrations. All right, so if you put all of this into your calculator, all right, if you put that into your calculator, you get 0.43 minus 0.42998 volts. So if you set this cell up where the concentrations equal equilibrium concentrations, you get a really, really big value. We're subtracting a really big value here. So 0.43 minus essentially, this number is essentially also 0.43. So our measured cell potential is actually 0 volts. All right? So when your battery achieves equilibrium, the forward direction is no longer spontaneous. What is equilibrium? Both the forward and reverse happen at the same time. That's not an electrochemical cell, all right? That we can't harness any energy from a system that's already at equilibrium. So here, your battery is dead. Once all of the concentrations are now equal to K, you don't have a battery anymore and your battery is dead. So E cell here is 0 volts. Your battery's dead. So tell me, what would delta G be if your battery is dead? 0. Right? Delta G is 0. And again, if you plug in to calculate delta G, remember delta G is negative NFE. So if E is 0, delta G is 0. All right, so the forward direction is not spontaneous. Your battery is dead now. Once your concentrations inside your battery are equal to your K equilibrium concentrations. Right? So really how batteries operate is, when you buy them new, they're at non-equilibrium conditions, so the forward direction is very spontaneous. But once your battery is dead, you've achieved equilibrium conditions and it's no longer useful to you anymore. Okay, so let's wrap all of these concepts up because we added this idea of cell potentials to other concepts we talked about in the last chapter, delta G and K, right, where we can relate the free energy change of an electrochemical reaction to this equation, where there's a factor of N and F to give us delta G. And so since E is related to delta G, E is also related to K. So Let's just kind of review the signs that we've been seeing to make sure that we are understanding the concepts of spontaneous redox reactions. Yeah. Oh, yeah. Yeah, rechargeable batteries. We'll talk about that in the end of the chapter. Yeah, okay. Yes. Rechargeable batteries is you plug them into a socket, you force the reaction backwards. So then when you unplug it, it goes forward again. That's what a rechargeable battery is. Okay. But some batteries, you can't do that. And we'll talk about that at the end of the chapter. All right. Okay, so what was I saying? Okay, the signs, yes. So remember, those knots that you see, they're no mistake. If you don't see a knot like delta G or E, it means we're at non-standard conditions. It's not that we forgot to put the little dot there. No, it means we're at non-standard conditions. Whereas the dot, or like the little knot next to the value, means that we are at standard conditions. So note here, we have delta G, K, E naught. All of these are at standard conditions and are related to K, the K value for that chemical reaction. Typically what we look for is that a reaction is very spontaneous in the forward direction as written when delta G is negative. We already learned that in chapter 19. The forward direction is also very favored if K is a really big number, because if K is really big, there's a lot of products present at equilibrium. Or E cell is very positive. All of those things are related to one another by these two equations, right? But if we're not at standard conditions, then we remove all of those knots from those values. But we can still calculate delta G and E at those non-standard conditions, either using the Nernst equation, or we can use, delta G equals delta G naught plus RT ln Q. So, So if we're at Q conditions, we use these different reactions here. So what we see as our reaction spontaneously progresses in the forward direction. So at standard conditions, remember, Q is equal to 1. But as the reaction progresses forward, Q starts to approach K. Q starts at 1 at standard conditions, but as it goes forward, Q approaches K. So yeah, we have that there. Q approaches K. What we see is that delta G approaches 0 as a reaction progresses forward. As our battery discharges, delta G approaches 0. And what we also see is that E cell, what we actually measure, also approaches 0 as well. Once we approach 0, we're at the conditions of Q equals K, right? Of what we actually measure given the concentrations that are present in our system. But note here that yes, delta G and E change for our chemical system, but the values of E naught and delta G naught do not change. Those are values from the textbook, right? But what we actually measure, in class or, in lab is slightly different because our concentrations can be different. All right, okay, so that's just kind of recapping the signs. So let's do a couple more using the Nernst equation. Okay, so let's do another one this time. I'll kind of show you the usefulness of line notation, okay? Line notation is just showing you exactly what is your anode, what is your cathode. That's kind of nice. All right, so we can use line notation to kind of cleanly show you what chemical reaction is happening. So here I have copper and silver. So copper, so remember how we read line notation. Copper is in which cell, which compartment? Anode, yes. So you always read it anode to cathode, left to right. So this side is your anode, this side is your cathode. Cool, we don't even have to think about it. Perfect. So that means if I give you these reduction half reactions, we can go ahead and calculate E cell. E cell naught, so at standard conditions. So E cell naught is simply going to be, so copper is our anode, silver is our cathode. So that means E cell is equal to 0.8 minus 0.34. So if we were at standard conditions, we would calculate or measure a cell potential of 0.46 volts. But are we at standard conditions? We are not. If we were at standard conditions, these two numbers, they would be what? 1 molarity, but we're not at standard conditions. So if we're not at standard conditions, we need to calculate the Nernst equation. We have to use the Nernst equation, so we need to calculate Q. All right, but I give you concentrations, I don't give you a balanced chemical reaction, so it's up to us to recognize what is the balanced chemical reaction so we can calculate Q, products over reactants. So I just did the flipping for you, all right, so I noticed, okay, copper is my anode, silver is my cathode, so here's my silver reaction. I flipped the copper reaction, so that is my balanced redox reaction. So the equation, the expression for Q in this reaction is copper 2 plus concentration over silver plus concentration, but that is squared. All right, so let's use the actual concentrations given here. If we are at standard conditions, it would be 1 over 1 squared, so Q would be 1, but we're not at standard conditions, so let's put in those actual concentrations. So I tell you that the copper concentration is 5 molarity, or 0.5 molarity, and silver is 3 molarity squared. So Q is equal to 0.0556. Perfect. So we're going to plug that Q into our Nernst equation. The last thing we need is to get N. So if you look at the two half reactions here, you can kind of quickly see what does N have to be. So tell me, what is N? 2, yep, because copper is losing 2 or gaining 2 electrons. What is it doing? No, it's losing 2 electrons. Silver, 1, so we double that silver reaction. So yeah, N is 2, and now it's just plug and chug, where the actual potential we read is 0.46 minus my Q conditions. 0.0592, is there 4? Yeah, volts over N we just got is 2, log of Q, which we just got is 0.0556. And so we get, when we plug all of that in, the measured cell potential that we actually read with our voltmeter at these given concentrations is slightly more, no, slightly less, nope, slightly more than what it typically is at standard conditions. And that kind of makes sense why our voltage is a little bit higher, because if you look at this, right now I have a lot of silver plus. Silver plus is a reactant. Right? So if you have a lot of reactant, you can think, oh yeah, that's going to push towards the product side a lot. Right? When we buy batteries, we are buying the reactants. We want the reactants because we want the reaction to proceed forward. If you buy a battery and it's all products, it's already discharged and it's dead. It's no good to you. Right? So in this case, yeah, we have a lot of reactants. So we see that E cell is a nice big number. We have a higher voltage than typical standard conditions. All right, let's do one more here, an interesting one. Here's another non-standard cell, but this one's a little bit different. So I show line notation again because, again, it's clean. So with this line notation, we see left to right, it's always anode minus cathode. Or sorry, anode and cathode, anode, cathode separated by that salt bridge. All right. And I have different concentrations here, all right? So we're going to use the Nernst equation again. So the process is the exact same. We need to get E cell naught first, so the cell potential at standard conditions first. We need to get N, and then we need to get Q. That's kind of the goal here. But what's peculiar about this? The anode and the cathode, they're the same, right? They're both copper. Isn't that kind of weird? Because in all our other electrochemical cells, they've always been different things. But here, it's the same thing. It's copper and copper. So what do you think the overall cell potential at standard conditions will be? I don't even actually technically need to give you this value, right? I tell you that the copper reduction half reaction potential is 0.34. But if the anode is 0.34 and the cathode is 0.34, when you subtract those two numbers, what cell potential will you get? 0, yes. So at standard conditions, this cell, when it's copper and copper, will read 0 volts. But again, are we at standard conditions? We are not. So yes, at standard conditions, this cell is 0, but we're not at standard conditions, so we need to actually plug in these values into the Nernst equation. And what we'll learn here is this is called a concentration cell, and you actually do get a small voltage that comes out of here when there's a concentration gradient. But what's hard is determining, okay, what is my Q expression? I know that Q is products over reactants, but the question is, well, which one is my product and which one is my reactant? So let's kind of take this stepwise, all right? In the anode reaction, this is oxidation. So look at the concentrations that are in your anode. In an oxidation reaction, copper solid loses 2 electrons to make copper 2 plus and releases 2 electrons. That's your oxidation reaction. So I tell you that this copper 2 plus is 0.1 molarity. That's your oxidation reaction. Your reduction reaction are these concentrations. So the reduction reaction actually involves copper 2 plus. It's being reduced. It's gaining 2 electrons, and it's becoming copper solid. And so copper 2 plus in the cathode, I tell you, is 1 molarity. So those are my 2 half reactions, and this will help you determine what number goes on the top and what number goes on the bottom in my Q expression. Because in order to balance this reaction, we add up your oxidation and your reduction reactions. So we see that which copper is the product. It's the one that's 0.1 molarity. The one that's the reactant is the one that's 1 molarity. So Q is equal to what? The 1 molarity goes where? On the top or the bottom? It's going to go on the bottom, yeah. So it's 0.1 molarity over 1 molarity. That is what Q is. Again, this is the product. That is the reactant. Product, reactant. All right? So we see that Q is equal to, what is that? 0.1. That is Q. Perfect. All right, and so now we have everything to plug into the Nernst equation. That was probably the hardest part, figuring out what Q is. Like, you recognize that it's products over reactants, but which one's your product, which one's your reactant, because it could be 0.1 over 1, or it could be 1 over 0.1, and you just don't know. So sometimes writing out the full half reactions will help you. Okay, so we just plug and chug. So E cell, what we actually measure, is equal to the cell potential at standard conditions, which is 0 for this, this reaction, because it's the same cathode and anode. But what actually gives us our potential is the concentration difference. So minus 0.5. I always forget what the Nernst equation is. 0.05, yes, 0.0592 over n. N is 2 in this case because 2 electrons are being transferred, log 0.1. And we see that this entire term right there is this whole term, when you calculate this, you get a positive 0.0296 volts. Or you can think like 29 millivolts or 30 millivolts is what you get. All right, so you get a little bit of potential just from having a concentration difference. So this is where I'm going to show that demo. All right, if we had this at standard conditions, if this was 1 and 1, our cell potential would be 0. We would measure nothing. But that's not what we have. Okay, so here, this is running at standard conditions. So what I have here is a beaker, and I can't touch it because I can't mix it. Here I have a beaker where it's very concentrated copper 2 plus on the bottom, but very dilute copper 2 plus on the top. So we have a concentration gradient. And I already have my electrodes in there already. So let's, I wanted to show my camera so you can like actually see the values. Okay, so I want to prove to you that right now, okay, can we read this? Okay, nope, can't do that. All right, can you read that? Yeah? Yeah? Okay, perfect. So right now, I don't have it hooked up. That's why it's reading basically 0. Let's try to not get there we go. All right, so right now I do not have the electrodes hooked up, so it's reading very, very close to 0. All right, so now I'm going to put the last electrode on here, complete the circuit, and we can see what happens once I complete this circuit in this concentration gradient. So what did we see? We see the number did, in fact, go up, right? It was kind of hovering around 0, like up and down around 0, but now it's very much a positive voltage. And again, we produce this voltage just from having a concentration difference of copper 2+, which is pretty cool, right? So what's producing that voltage is that Q value, all right? That small Q value and that concentration difference. What do you think will happen if I mix this container up? Will I have a concentration difference anymore if I mix it up? No. If I mix all of this up so the concentration's uniform throughout, what does Q become? 1. Yeah, so let's see what happens. Come on. Go. Mix. Yeah, so I'm mixing it up, and that voltage is definitely going down. Come on. Go down. It's such a small voltage that it's hard to get that to happen. But yes, once that Q is 1, we should see, oh my gosh, why is the voltage going up? Let's see. It's going down, right? Yeah, it's going down. Once I mix it up, Q approaches 1 and the voltage should go down. All right, so there's our concentration cell. Perfect, okay. So we got 10 minutes left. Let me just introduce batteries a little bit, because there's questions about that. And I think batteries are cool, because it's application of electrochemistry. So remember, we'll just go in a little bit of this. I'll point out that, yes, chapter part 1 homework is due on Monday now. That's the assessment for midterm, the last midterm, midterm 4. We'll work through the rest of these chapters rather slowly and incorporate a lot of review. But I like this part of the chapter because we're applying a lot of what we've been learning about. Positive cell potentials, harnessing the transfer of electrons. This is important for battery operation. All right, Honda is building a new EV plant in Ohio. It's in Grove City. They're pumping billions of dollars into this economy. I guarantee you someone in this room is going to work for Honda in that Honda plant, probably. This application is very important in that growing industry, electric vehicles, batteries. And there's kind of some things we need to think about, like, yeah, we want the most power, we want the most voltage and things like that, but there's factors we want to think about. Okay, so the question was batteries. Yes, we harness in a battery the spontaneous forward direction. Okay, so how batteries work is that they're just portable electrical self-contained power sources where we can harness those transfer of electrons. We're harnessing that spontaneous forward reaction. So here you can think of these beakers as batteries too. It's just they're not very portable. All right, so in a battery it's all self-contained. So there's basically two genres of batteries that you're going to interact with in your life. Primary batteries and secondary batteries. Primary batteries are non-rechargeable. Those are your cheap alkaline batteries that you buy at the checkout lane of Target. And usually they're less than $5. Okay. Secondary batteries are rechargeable batteries. You can probably buy them at the checkout lane in Target too, but they're going to be a lot more expensive. And the reason is because they're rechargeable. But they're rechargeable because a different chemistry is going on. You're still harnessing that forward direction of the spontaneous reaction. But the idea here is when you use a battery, reactants become products. But once it's a product, you can't have any more energy. All right? So what a rechargeable battery does is you're able to plug your battery into a socket, convert your products back to reactants so you can use it again. But you can't do that in a primary battery, in a non-rechargeable battery. And here's the reason. It's because you can't just plug it into a socket and the reverse reaction happens. And it's because of the nature of using cheap materials that are not reversible. So yeah, I like to think of primary batteries. These are your cheap alkaline batteries. So they go to A to B to give you like a nice voltage or whatever. Those are like your Duracell batteries. But when you plug them into the socket, You don't go back to A. B doesn't go back to your reactant. B actually becomes something else. It like becomes C, which you can't recharge. Like you can't actually harness that energy again. But for a rechargeable battery, when you discharge it, A goes to B, and then when you plug it into a socket, B goes back to A when you plug it in. All right, plug in. But in this one, in a primary cell, when you plug it in, it just becomes something else that you can't actually harness the energy. I don't know if you've ever tried to put a cheap alkaline battery in like one of those like recharger stations. It doesn't work, right? You can put it in there, but then when you try to use it, it's still going to be a dead battery. I've tried that because I'm cheap. But it doesn't work. You have to use a different type of technology, which we'll talk about in secondary cells. And then we'll also talk about fuel cells. It's kind of like a type of battery. It's a new up and coming realm of energy storage, and that's hydrogen fuel cells, but it is a little bit different. Okay, so let's talk about the first two. And there's actually just a lot of review in here. All right, I want you to be better members of society, so understanding how batteries work is kind of important and just, yeah, makes you sound smarter here. So here, our first one, alkaline batteries. These are our cheap primary batteries. It's a primary battery, meaning it's not rechargeable. These are your Duracells. Here is the half reactions that are involved in a Duracell battery. We have our anode at zinc, and the cathode is manganese. So why do you think we call it an alkaline battery? Alkaline means what? Basic, yeah. And this reaction looks like it's balanced in what kind of conditions? Basic conditions, yes. So I give you the half reactions, I tell you the anode and the cathode. Tell me, what is the predicted cell potential at standard conditions for an alkaline battery? So it's cathode minus anode, so it's positive 0.15 minus negative 1.28 volts. And so we see that for an alkaline battery, the predicted cell potential is 1.43 volts. Right, cathode minus anode. All right, let's look at the lead acid battery. So lead acid batteries, these are the batteries that are in like your car and your vehicle. It helps you, start your spark plugs to start your engine. So here, a lead acid battery is not in basic conditions. It's actually balanced in acidic conditions. So that's why it's called lead acid, that there's a lot of sulfuric acid present. So here, we can do the same thing. Let's calculate the cell potential of the overall cell given the anode and the cathode. So here, the cathode is lead oxide, so 1.69 volts minus the anode negative 0.36 volts. So we see when you add those two numbers up, you get something like 2.05 volts, right? So if you look at the voltage given by the manufacturer of your alkaline battery here, voltages of one cell of the lead acid battery is usually closer to 2 volts. You might notice as well, why are our calculated values not necessarily what the manufacturer shows? Remember how we calculated this, cathode minus anode. That only works at what kind of conditions? Standard conditions. So do you think batteries are manufactured into standard condition concentrations? They are not. They're probably going to pack a lot higher concentrations in there than just 1 molarity. So yeah, our calculated E cells are different because when these batteries are made, they're not at standard conditions. Standard conditions. So that's why they're a little bit different, okay? So alkaline batteries versus lead acid batteries, it's funny, when folks talk about batteries and like devices, let's say like you go to an old remote or something at your house and you change the batteries in it and you open the cover and you see a lot of crusty stuff in it. You ever see that in the battery compartment? And you ever hear someone go, oh, be careful, that's battery acid. Don't touch it. It's battery acid, like wash your hands. But based upon, like, think about it, cheap Duracell batteries. Actually, Duracell's pretty expensive. Just a cheap primary battery. Based upon what we learned right here, we call them alkaline batteries. So when you open up the battery compartment of a device and it's all crusty, is it acid? Is it battery acid? No, it's not. It's battery base. So the reason alkaline batteries are cheap is that these reactions, they're not reversible once you plug it in, but for a lead acid battery it is, and so when you plug it into the wall or hook it up to your alternator, the reverse reaction happens, so the forward can happen again. So have a great weekend. Remember, chapter 20 part 1 is due on Monday. We'll finish this chapter on Tuesday.